Growing up, my mom would always make red velvet cakes. I mean, they were my favorite. I remember when I became an adult, I started making them for my own family. In fact, soon after I first met my mother-in-law and my father-in-law, I brought them a red velvet cake. I think that's how our relationship hit it off. I had pretty much committed this recipe to memory, but I would always get confused as to whether I should use baking soda or baking powder. A quick call to my mom would often clear it up, but on this one day, I couldn't reach her. So I thought to myself, it's only a teaspoon. They both do the same thing. Baking powder it is. Well, I was wrong. My experiment had failed. I mean, the cake, it didn't even rise. It was tough, and it ended up in the trash. Now, what I learned that day was this. To successfully make a red velvet cake, I had to take several factors into account. Things like ingredients, and oven temperature, and baking time. And if I vary any one of them, even slightly, I might not get the result I was anticipating. Well, my mother had perfected the experiment of making a red velvet cake, and her recipe was my experimental design. Now, much of the data that we've analyzed throughout this course has been the result of statistical experiments that have been well designed and planned far in advance. However, as I quickly learned while doing my very first consulting job, if you've got problems with an experiment's design, or if there are data collection methods that are biased, well, those often occur before you ever start the analysis. You then have to go back and spend more money to collect more data in a way that's going to meet your underlying assumptions of our statistical methods. Well, I want you to avoid having to do that, if at all possible. So, in this lecture, we'll gain an understanding of how experiments should be designed so that we collect sound statistical data. All right. Remember, uncertainty or random error is all around us, and it's in every one of our measurements. It's unavoidable, but we've learned ways to estimate our uncertainty. We know that we can minimize uncertainty with better instruments or more accurate measurement techniques and whatnot. So what are the steps that we need to do to properly plan and conduct our experiment? Those steps are going to closely follow the scientific method. First, we state the problem. Okay? My problem was making a pretty good red velvet cake. And how do I do that if I alter the ingredients? Second, I want to decide on the explanatory and the response variable. So what variables am I going to leave fixed, and which ones am I going to change? Third, I want to design and conduct the experiment. Fourth steps, I'm going to analyze my results. And then my fifth step is to draw a conclusion. Now, it's important that we take the necessary time and effort to organize the experiment appropriately, because you want to have sufficient data to answer your question. And now this process of going through and making sure that your question's organized and you have the proper data is called experimental design. Let's start with some basic terminology. First, a factor. A factor is just an independent controlled variable. For example, maybe the type of drug, or a temperature, or marital status. Those are all examples of a factor. Second is treatment. A treatment is just a specific value of the factor that's going to give us the factor breakdown. So for example, single, married, divorced, widow, those are all treatments in the factor of marital status. And then variables. So our variables are going to be all of the factors, all of their treatments, and all of their measured responses. There are several types of factors that might occur in our experiment, including the following. First, experimental factors. Now, these are going to be factors that get assigned at random to our different treatment levels. So like temperature or the amount of a particular drug. Second is classification factors. Now, these are factors that represent unchangeable labels like sex or age or even race. Now, experimental error. This is the variation in our responses among the experimental units that are going to be assigned to the same treatment, and they're observed under the same experimental conditions. So this experimental error is something that we're always trying to quantify. Now, ideally, we would like the experimental error to be 0, but we know that's impossible for several reasons, including the fact that, well, there's going to be variation in just how our measurements were made. And secondly, there are always those extraneous factors other than the treatments that are going to affect the response. Okay, well, now that we've got the basic terminology, we can now start to discuss techniques for effective experimental design. And we're going to talk about two well-known experimental design models. First is the randomized block design, and second is the 2 to the K Factorial design. Okay, so as we start to think about designing our experiment, the first technique that we have to keep in mind is randomization. So remember, your treatments should be allocated according to our experimental units randomly. Remember how Fisher allocated his fertilizer plots? It was in a deliberately random way. Now, the main reason that we randomize is because we have to negate the effects of any uncontrolled extraneous variable. And we do that by making sure that the sample is representative of the population. We also eliminate any possible effects of systematic bias. So yay, randomization. Now, the second technique you're going to think about as you do your experimental design is that of replication. Replication tells us the number of samples that we have to take for each treatment. Now, when we increase the number of replications, we actually collect more information about our treatments. So this is a good thing. Now, what replication does is it's going to give us the power to reject our null hypothesis, that the group means are all equal to 0. And it's also going to help if we've got missing data or possible outliers. So it helps to have replications in our data so that we can account for those. Now, when possible, we want to base our theories on reproducible results. And although this last reason applies more to replicating your whole study than just a larger number of samples in it, the more replications we have, the more variability we can actually observe in our response variable. And we can separate that from the treatment effects. So when we increase the number of replications, we increase our reliability in the outcome. All right. So in order to show that two treatments have different means, we have to measure several samples given the same treatment. That's the benefit of replication. Now, the next technique is known as blocking. Now, blocking refers to the distribution of our experimental units into blocks, right? And we're going to do that in such a way that the units within each block are going to be homogeneous. So in order for our blocking to be effective, our experiments, well, they should be arranged so that the within block variation is smaller than the between block variation. Now, there are several different types of blocking techniques, and the most common blocking technique is called the randomized complete block design. So when participants within a given block are randomly assigned to, say, one of the treatment groups, and this process is repeated for every one of your blocks, then that design is called a randomized block design. Now, it's random because your experimental units are randomly assigned to each block, and it's also complete because each treatment is included in every single block. Now, assignment of experimental units to these blocks and to the treatments has to be random. Now, blocks of these units are created to try to control for known sources of variation in the mean response among those experimental units. For example, let's go back to Fisher's agricultural data. We might block the field plot according to, say, nutrient gradient or water moisture gradient, and then also maybe soil composition. Here's an example where we have 4 blocks that vary according to the water moisture gradient. We've got 5 treatments, which might be maybe 5 different types of fertilizer, and we arrange the block such that the fertilizers rotate within the block while being represented at each moisture gradient level. Now, another technique we consider is the sample size. The choice between the sample size and the cost is always going to be a compromise, unless, of course, you have infinite resources. Now, anytime we take more measurements, we increase the reliability of our results. So this is a great thing. But in doing that, we usually increase the cost of our study, which is problematic. So this is the reason that we take a sample from the population to make inference about population parameters, because we can't afford to sample the entire population. Now, if we have pairs of subjects, maybe perhaps twins or subjects with similar demographic variables, then what we can do in that case is randomly assign one treatment to one subject and the other treatment to the other subject. Now, this works particularly well if there are only 2 levels of a factor that we're interested in. Now, there are several advantages to a blocked design. And first, it's going to allow us to control for a single source of variation. And it lets us remove that effect from the experimental error. So that's a good thing. And second, it gives us a lot of flexibility in how we decide to lay out our experiment. However, a disadvantage might be that if we've got a large number of treatments, then it can often be difficult to fit all of our combinations within a block. So we may not want to use a block design in that case. Now, what does ANOVA look like in a randomized block design? Well, here's the output. Notice that the first column has the source of the variation. Either is source due to treatment, source due to blocks, source due to error, or the total. Now, column 2 gives you the associated sum of squares. The sum of squares for your treatments, for your blocks, for your error, and for your total. Notice in column 3, here we get the degrees of freedom. A minus 1 for our sum of squares treatments, B minus 1 for the sum of squares blocks, A minus 1 times B minus 1 for the error, and N minus 1 for our total degrees of freedom. And the fourth column gives us the mean square. So we've got the mean square for treatments, which is your sum of squares treatments divided by A minus 1. The mean square for your blocks, which is your sum of squares blocks divided by B minus 1. And then your mean square error, which is your sum of squares error divided by A minus 1 times B minus 1. Now, under the null hypothesis, our group means are all equal to 0, and there'd be no treatment effect. And if our F ratio is close to 1, meaning our mean square for treatment is close to the mean square for error, then we fail to reject the null hypothesis. Otherwise, if there's a valid treatment effect, then that mean square treatment is going to be large when you compare it to the mean square error, and our F statistic will allow us to reject the null hypothesis. Now, a factorial design, well, this time we use that to evaluate 2 or more factors simultaneously. When we have a full factorial design, we're going to vary one of our factors at a time while holding the other one fixed. And then we're going to do our full experiment as we vary that one factor. For example, I might vary the amount of flour in my red velvet cake by making it with either 3 cups or 2 cups or 1 cup. And I would leave all the other ingredients fixed. Now you can imagine if we did this for each ingredient, well, it would take a lot of time and it would waste a lot of resources. So when you've got several factors that you think might affect your response, it actually helps to start with a simple design where each factor can have just 2 levels. So for example, in our red velvet cake, we might test the presence or the absence of a particular ingredient and see how that changes our cake output. Well, this leads us to the popular 2 to the K factorial design. Here we've got K factors, each with 2 levels, and that gives us 2 to the K treatment combinations. Now, the full 2 to the K factorial design uses all of those 2 to the K treatments. And actually, it requires the fewest runs of any factorial design for K factors. We often use this 2 to the K design at an early stage of factor screening because it gives us an idea of which factors are going to be most significant in our experiment. Now, the 2 to the K factorial design is especially useful when we've got experiments that involve several factors, where K is our number of factors. And if we need to study the interaction of those factors on a specific response. Now, each of the factors has 2 levels, typically is low or high, and it can either be quantitative or qualitative. Now, this 2 to the K factorial design is particularly useful in the early stages of your experiment. You've got several factors you want to investigate, and you need to minimize the number of your treatment combinations or your sample size. So it helps you save money when you do this 2 to the K design. It's also helpful if you need to study all K of your factors in a complete factorial arrangement. So this design collects data at all possible combinations of all factor levels. But remember, you've only got low and high. So for each factor, there's only 2 possibilities. So that's what keeps this design simplified. Now, as your K gets larger, your sample size is going to increase exponentially. So designs that go beyond a K equal to 5 or 6, unfortunately become infeasible. But let's look at the simplest design, 2 to the K, where K equals 2. Now in this case, you've got 2 factors, say A and B, and each factor has 2 levels, low and high. And so we're interested in 3 things. We want to know what's the main effect of A, what's the main effect of B, and then how do those 2 things interact? What's the interaction effect of A and B? Now, in the simplest case where K equals 2, we've got 4 factor levels. So in trials 1 and 2, we're going to fix A up high, and we're going to vary B between high and low. And then in trials 3 and 4, we're going to fix A down low, and then we're going to vary B high and low. Now, can you write out the case for K equal to 3? Let's do that together. Since 2 cubed equals 8, we know we're going to have 8 factor levels. Now, each factor should be low 4 times and high 4 times, and that's going to give us all possible combinations. All right, let's begin by first specifying the first 4 of factor A to be high. We'll use pluses and minuses. So plus, 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 which is going to require the last 4 factors of A to be low. Minus, 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 minus. Great. So once we've got A factored, we now have to let B factor within A. So for A's 4 positives, B is going to be negative twice, minus, minus, and then positive twice, plus, plus. Likewise, for A's 4 negative terms, B is going to be positive twice, plus, plus, and negative twice, minus, minus. So now all that's left is we have to factor in C. For A, both positive, and B, both negative, factor C comes in as a positive and a negative. Likewise, for A, both positive, and B, both positive, factor C comes in as both a positive and a negative. Do you see the pattern? Now notice here, for A, both negative, and B, both negative, factor C comes in again as a positive and a negative. And then lastly, for A, both negative, and B, both positive, C comes right back with a positive and a negative. Right? You've just written out your 2 to the K factorial design for K equal to 3. All right, if you're starting to get overwhelmed, don't worry, because R can actually help you build your 2 to the K factorial design. Let's load the BHH2 library, and we're going to run the command print x equals FF DES matrix. That stands for design matrix. And here we're going to look at where K equals to 2. So we'll evaluate that at 2. So this is going to give us the design matrix for a 2 squared factorial design. Notice here, here's our 4 factorial design that we already came up with. So low and low for the first row, and then high low for the second row, low high for the third row, and high high for the fourth row. So here -1 tells us that the factor should be low, 1 tells us that the factor should be high. And notice that R gives you all of those possible combinations. All right, what happens when K equals 3? Well, that's our 2 to the 2 cubed factorial design, which gives us 8 factors. And notice that R gives us nicely what that design would look like for all 3 of those factors. Okay, we don't have to stop there. Let's look at 4. Wow. So here you can see R is giving us the design matrix when K equals to 4. And that gives us 16 possibilities. And lastly, we see here when K equals to 5. Now here you can tell this is becoming a bit cumbersome, and it might not be an experiment that we want to do by hand. Once we go above 4 or 5, we may want to think about other methods to do our design of experiment. Now, once our design is specified, we can actually use our data that we've been collecting, and we can do the experiment similar to how we've been doing ANOVA or ANCOVA or MANOVA. So those techniques we've already covered. Let's see an example of how it applies to a design of experiment. Here's a shoes data set. The shoes data set contains a list of the wear of shoe materials, A and B, for 1 foot each of 10 boys. Now, it's in the package BHH2, so if you don't already, have that installed and load the library. Next, we're going to bring up the shoes data. So data of shoes.data. Let's look at a summary statistic of that data. Here you see we've got in the first column boy. So there's a total of 10 boys in our sample. And then material A, material B. And so for material A, the boys, 7 boys wore material A on the left foot, 3 boys wore material A on the right foot. And then you see the wear of material B, and notice that 7 boys wore material B on the right foot, and 3 boys wore material B on the left foot. And then you see their appropriate ranges of wear. So for instance, for material A, it ranged from 6.6 to a maximum of 14.3 with an average wear of 10.6. And material B ranged from 6.4 to a maximum of 14.2 with an average wear of 11.04. All right, we can do an analysis of variance to see if boy is related to the materials of A or the materials of B. And if we use this star, look at that, mat A, star mat B, that's telling R we also want to see, is there an interaction? Okay, so let's run this command. Shoes.AOV is equal to AOV of boy on mat A, material A, star mat B, material B. So that's going to look at the effect of material A plus the effect of material B plus any interaction effect of the two. Our data comes from shoes data. A summary of AOV gives us the following results. We see each of our variables, so mat A, mat B, the interaction, and the residuals. And you see their associated degrees of freedom. 1 degree of freedom for mat A, 1 for mat B, 1 for the interaction, and 6 that are left in near residuals. Look at those sum of squares. We've got a pretty low sum of squares. So 0.89 for material A, 3.13 for material B, 8.77 for the interaction, and 69.7 left in the residuals. Notice your mean square error, which is the sum of squares divided by the degrees of freedom, and your F values. So those F values ought to jump out to you because remember, that's the ratio of our variance. And when those are close to 1, that tells you that there's not a difference in the groups. Notice here we get F values that are even less than 1 and P values that are not significant. So this output is telling us that material has no effect on the different feet that the boys wore them on. Now, but here's a possible pitfall here. As we mentioned previously, we can use blocking to control for a parameter that might not be of immediate interest, but one which has to be accounted for in our analysis. Now, but don't forget about ANCOVA, because it's possible that you could actually save a step and use analysis of covariance to measure and remove the effect of a factor from your analysis. Now, we would only have to adjust statistically to account for the covariate, whereas in blocking, we actually have to design the experiment with a block factor into the design from the start. And that's the big point here. Cleaning up your data after the fact with ANCOVA is nice. But it's even better to design your study from the start to remove or even control for the covariance or any unwanted categorical factors. A good experimental design gives you data that lets you focus more sharply on testing your main outcome of interest.